Meet the Fellows event. So we have 5 talks given by fellows in the Logic and AI for Databases program. The first talk is by Remy Wang, who will tell us about relational programming.
Thank you. Okay, so by myself, I recently graduated from UW, working with Dan Suchu. Right now at Simmons, joining UCLA next year as an assistant professor. And I think we've seen a lot of math, a lot of words today. So I'm going to begin with a small history lesson. Right. So about 100 years ago, computer science started with a dream. This guy, David Hilbert, wanted to do this thing, which is understanding the world with reason. Right? This is by the end of the First World War. So people were going a little crazy. So Hilbert thought that we could benefit from some reasoning. And because Hilbert is a mathematician, or was a mathematician, to him, the world means math, and the reason means logic. So this was the well-known Hilbert's program, which is trying to build this formal foundation that based on logic for mathematics. So soon after, not very long after, these 2 people came, and Kurt Gödel and Alan Turing basically came with results saying that you cannot do this, right? So first of all, we have the incompleteness theorems of Gödel saying that you cannot have a formal system that's both consistent and expressive enough to express arithmetics. And then Turing also came along with his halting problem, which showed that it's a negative resolution to the Einstein's problem, saying that you cannot have a machine that just proves all of math if you just run it. Right? So on the surface, this was kind of a blow to our dream of understanding the world with reason. But I think this is actually a really fantastic thing, right? Because from the result, we got computers, which are really magical machines that make our dreams come true, and then make our wildest dreams and something that we didn't even dare to dream of come true. So in a sense, we, instead of understanding the world, we're reducing math to logic. We're able to change the world with logic. But not so quick, right? In the beginning, the way we program these machines are really painful, right? So these are some of the pioneers of programmers working on the first computer called ENIAC. And then they were literally patching the cables with their hands in order to put in the bit patterns in terms of programs. Right? And then later on, we got a little better technology. So we have the punch cards, where you can enter numbers, which basically represent assembly code. And it was not until the 1960s that we had this Cambrian explosion of programming languages that really increased our productivity. So here's kind of a sample of all of the different flavors of PLs that came out around the time of 60s and 70s. Right? But what we're here to talk about today is not any of these pictures. It's ideas of just using logic. You know, we're going back to Hilbert's program. Can we just use logic to express what we want to compute and what we want to tell the computer to do? And then indeed, we can. And then, so people came up with some programming languages. One is Prolog. On the other end of the spectrum is actually SQL or SQL that are based on this logical foundation that let us program our computers. So these languages are on kind of 2 extremes of the spectrum. So SQL is immensely successful. So if you have a smartphone, it's running SQL right now. This is running SQL right now. This is running SQL right now. So it's everywhere. It runs the world, literally. And then it works because it's really, really fast. And then, you know, tech people were addicted to efficiency. Right? So on one end of the spectrum, this is really fast, but it's really limited in expressiveness. So on the other extreme, Prolog is a Turing-complete language, meaning that you can basically write any program you want to write. So it's really expressive. But as a drawback, you know, it kind of suffers in terms of efficiency as compared to SQL. So one of my research projects is on this, picking this sweet spot in the spectrum between expressiveness and efficiency. And then we designed this language called Datalogo, which is an extension of Datalog with the power of Semirings. So on the expressive end, we took some great ideas from before. So we have the recursive rules from the data law language, and then we have the summary rings, which allows us to express computation over a very rich data type. So this allows us to express a lot of really useful computation like matrix algebra, linear algebra, and then shortest path algorithms over graphs. So we have recursion and aggregation at the same time. So on the other consideration for efficiency, right, so we also look at algorithms for the relational join. So join is really important because that's basically the operator we use to run any database query. So it's a generalization of functional composition as relation is a generation of functions. So this is really the bread and butter of relational databases. And then we also look at ways to optimize data logical programs. So this means that you give me some really high-level intuitive program, and then I will rearrange operations to make sure that it runs very efficiently. And then outside of the context of kind of database and data log, I also work with my colleagues in programming languages. And then we developed this idea of using tree automata to optimize programs. So I'm going to go into a little bit more detail on that very soon. So here's a kind of sample of the problems that I'm interested in. So I think some of these are open, some of these are might be not. I'm not a theorist, so I don't know. So if you tell me some of these are already solved, that will make me really happy. Where if it's not, if it's open, that will make you very happy because you can solve it. Okay. So one of the examples is that look at this. It's just a finite state automaton, right? So let's look at the string case. So there's a string automaton, and if we just treat this automaton as a graph, so ignore the labels on the edges and the states. So we treat each state as a vertex, and then we treat each transition as an edge. Then suppose we want to find the shortest path from the starting stage to the acceptance state, right? So it's right here. Right? We can go through here to here. And if we do this for some kind of automaton, and then we think of these paths as having cost to each symbol, that essentially lets us extract the cheapest string that's represented by the language, right? So that's a string case, and then in the string case we have the automaton as a graph. So overall search path is pretty fast. A cubic time or quadratic time is still pretty fast. But for programs, we actually need the so-called tree automaton. So these are generalizations of a string automaton to accept a language of trees inside of the strings. And then over there, the problem basically becomes we want to find the cheapest tree, or the lowest weighted tree represented by the automaton. And then over there, we basically need to solve this shortest hyperpath problem. And then as far as I know, there has been some early algorithms actually by Donald Knuth solving this in pretty efficient time. But then when you have kind of paths consisting of hyper edges, there's a question of do you double count an edge that's used twice, or do you only count it once, right? So basically, one problem is shortest hyperpath on tree automata. So another kind of shortest path flavor problem is the so-called algebraic path problem, and I think it's really elegant because it's a very general problem, right? So the input is a graph, which is vertices and edges, and then two sink and target vertices in the graph. And then what we want to do is to find a regular expression over the edges in the graph, such that the regular expression represents all possible paths from S to B in the graph. Right. So once you find this regular expression, this really symbolic expression, you can evaluate it over different summary rings to solve, shortest path problems and then some kind of flow problems. Right. So there's been algorithms. One of these is by Bob Tarjan, saying that if your graph is so-called reducible, then you can do this in almost linear time. So alpha here is the reverse Ackermann function. Right? So I'm interested in saying that like not a lot of database graphs are actually reducible. So on these graphs, can we get some property so that we can also get efficient algorithms like this? Yeah.
For the M alpha bound here, is it optimal for reducible?
For reducible graphs, I'm not sure. Yeah, but it's basically linear, so I don't think you can do much better. Okay, and then here's a pretty straightforward question. So find the sparse homomorphic image of a hypergraph. So homomorphism is kind of standard. It's a mapping from vertices to vertices, such that if there's an edge between two vertices in the source, you should have an edge in the target graph, right? So here we have a trade-off of we want the image to be as small as possible, but we also want it to be sparse, right? So you can always map everything to just like a single vertex with a stealth loop. So you just map all of the vertices to the same vertex, and this is fine, but it's really dense, right? It's really small but really dense. So we want to find this this sweet spot in the trade-off space. Okay, so going back to Hilbert, he tried to understand the world with logic, but I invite you to change your world with logic with me. So, thank you.
Thank you. Any questions?